thanks for coming. I think I was chatting with him about how good it is to see a Java user group like getting together in a monthly basis. That's very interesting. I'm originally from Brazil, so there's this Java user group called So Java. I think, not sure if you have heard of. So back there, we used to have those meetings kind of on a monthly basis, but currently I'm living in Raleigh, and North Carolina is kind of doesn't seem to be really interested in getting together so frequently like you guys are doing. So congratulations to you. That's quite an accomplishment. My name is Ricardo, right? So as I said, I'm originally from Brazil, so that's why you're gonna feel this weird little accent that I have. And not only because I'm from Brazil and I'm speaking English, but because in Brazil I'm from different parts. I basically lived like 10 years on 3 different cities, and the accents kind of change a lot when you speak Brazilian Portuguese. So now I add English, so that's kind of a very interesting mixer on it. Remember when I told you that Confluent is hiring? So let me explain what Confluent is, because I work for this company, right? So Confluent is a lot of things, but it's mostly known because, number A, it is primarily the company that develops Kafka as an open source project. So basically we have more than 85% of the commits of the technology, not only the Kafka as a cluster, but the open source projects around it, like Kafka Streams, Kafka Connect, obviously the clients, right? Both the Java clients and the non-Java clients. But also, Confluent is kind of known because it is the company that has been founded by the creators of Kafka. So Kafka, not sure how many of you know about the story about Kafka. 10 years ago, LinkedIn, they were trying to solve some integration and data problems on LinkedIn, and then they come up with this universal backbone that is scalable, that's fast, that has very good throughput, and it eventually became Kafka, right? So they left LinkedIn and they founded Confluent. So that's what Confluent basically does, right? We provide enterprise-ready distribution of Kafka, as well as native cloud service for Kafka. So that's what Confluent does these days, right? I'm going to show a little bit of what we do during the pack demo that we're going to do, right? But as I told you, Confluent is hiring, and I think you are better off positioned here because most of you live here in the, not Bay Area, but California in general. Our headquarters is in Mountain View, but as long as if you live in California, you'll be more than okay if you're looking for a position for an engineering perspective, right? So that's lots of position for Kafka Streams, Kafka Broker, CREs, if you're into upsides as well. So I can talk later about what positions are open, right? This presentation, I'm pretty sure that everybody kind of was aware that we're going to play Pac-Man in the presentation. I think you saw the title of the presentation, and we are going to do this, right? Rest assured that we are going to do. But more importantly, the objective of this presentation is to teach a very complicated term that at Confluent we are trying to bring to the communities these days, which is this. I'll come back to this. Event streaming, how many of you have heard about this? Like, it's funny because 2 weeks ago I was in the Microsoft Ignite conference in Orlando, and we had a booth there, and we were obviously presenting what Confluent does, and I promise you, more than 85% of the people that came by to our booth was asking us this. What we do is basically what Netflix does. Oh yeah, that's streaming, yeah, I think that's the same what Netflix does, or Disney Plus, or something like this. So no, that's not that type of streaming that we do, right? Event streaming is a new way to store and process data, right? So there's a new technique, and the objective of this presentation is to show you how it looks like, all right? So our team, I'm part of this team called Developer Relations at Confluent. So essentially, I'm a developer advocate. And our team kind of had this objective of reteach Java to communities. Either Java user groups, big data communities, machine learning communities, because raise your hands how many of you think that Kafka is a messaging technology, and don't be shy. That's so good, right? So basically 2 people, that's not bad. I think San Diego Java user group, there has always smart people. I knew that, right? Kafka is not a messaging technology, and the creators of Kafka, like 10 years ago, they've made a mistake of not worrying and explaining better what Confluent is about. No, sorry, not Confluent. What Kafka is about, right? Kafka is an event streaming platform. the type of problems that you would solve with Kafka is beyond just messaging. Because let's face it, what's messaging? It's moving data from point A to point B, right? That's messaging, right? Whether if you're using for implement some sort of a buffer to your microservices, or maybe you were solving some integration platform that you were moving data for other applications to consume the data, but messaging moves data, right? Streaming, on the other hand, is not just about moving data. It's about storing data, point number one. It needs to be persistent. For example, pretty sure some of you might have written some ETL programs before, right? Either in Java, sorry, go ahead.
As in Kafka Airflow?
No, Apache Kafka. Yeah, the open source project called Apache Kafka.
So not the data engineering tool Airflow?
It can. Oh, yeah, I know Airflow, but not necessarily is related. Although basically the challenges that Kafka helps to solve is similar to Airflow, I would say. Yeah. Think about Kafka, and you're going to see this in the presentation. Think about Kafka like a ETL, like extract, transform, load, that you would do with typical databases, programs, but ETL by nature is batch, right? So you store data in your database, in your transactional databases, and you are going to create those programs, that batch programs that's going to load up from the transactional database, and it's going to write into a data lake, data warehouse, somewhere where you're going to do the analytics, right? So think about it. Why do we do this? Why don't we do the analytics in the transactional databases? Have you ever think about that?
Real-time data processing.
No, correct.
Batch, where Airflow is batch.
Airflow is batch, correct. But if you think about it, why don't we do analytics directly on the transactional database? Because it's going to slow down the database. The database was not able to store data and process the data concurrently, right? And this is by design. I mean, the databases were not made to actually store and process at the same time. Go ahead.
Databases are like NoSQL, MySQL.
Good questions. When I say databases, I'm referring both to SQL databases like MySQL, Postgres, or DB2, or Oracle, and NoSQL databases as well. Cassandra, MongoDB, or whatever, NoSQL databases. They're meant to store data and to retrieve data for later processing, right? But we're dealing these days with applications that cannot wait about, all right, let's wait for the job that runs every midnight to load the data and transfer for the data warehouse so then we can start processing the analytics, right? We have to reduce the latency of this. And the way to solve this problem is not using a different type of technology, but a different type of strategy of implementation, which we call event streaming, right? So the presentation today is going to be how event streaming applications look like, right? Because as developers, I mean, everybody here can say this, as a developer you have to start with an example, right? I mean, if you start learning with a technology, give me an example, a hello world or something simple that I can see how it looks like and I can replicate to my own world, right? So what I've brought you today is an example of event streaming application, and guess what? It's going to be like playing Pac-Man, all right? So, any questions so far? Okay, so what we are going to do, I brought this, oh yeah, that's the face that people does when we talk about event streaming application, that basically the facial expression that you are not clearly understanding what we are talking about. So that's what we are trying to solve, to remove that facial expression from you, all right? So this is a conceptual view about what we are going to build. I'm not going to fully rely on slides for the presentation. I don't like that. I like to be hands-on. So basically, we are going to deploy from scratch the application so you can see step by step the application being built, right, and being deployed, right? But basically, after the application is deployed, you are going to play Pac-Man game with your phones, or if you have laptops, I would actually encourage you to use the laptops because it's better to play the Pac-Man with the arrow keys of your keyboard. You can use the mobile phone as well, but the mobile phone, I don't know, I don't like that much, right? And the events from your games, each one of your games, is going to be stored into Kafka topics. All right? So I'm going to store this data, let's call data for now, but I prefer the term events. We're going to store this data, and then I'm going to process this in near real time and come up with a scoreboard. Okay? But what is the difference of this scoreboard? This scoreboard is going to look live, right? It won't be that static data that we usually store in databases. Like, for example, if someone is maybe the #1 in the position, but someone else kind of got a higher score, you're going to see the change of the position alive, right? So that's the main difference about programming oriented to jobs or batch and programming oriented to event streaming, right? Event streaming allows you to see data live, okay? So you can take decisions much faster than in the older world of doing jobs, all right? So far so good? That's the conceptual view, right? The architectural view, we're going to have this application running in your mobile or computer, right? Every event that emits from the game itself is going to call an API. Let's call it API for now, all right? And this API jobs is basically right into a Kafka topic, okay? There will be this engine, okay? Let's call engine for now, right? Later on, we're going to actually drill down into the implementation details, and you're going to see what this engine actually is, right? But the job of this engine is essentially to process the data as they flow into Kafka, right? And to produce an output, which is going to be stored into another Kafka topic. So, input topic, output topic, okay? Just like we would do in a ETL or batch program, right? We have input tables, we have the program that does batch, and that program flushes the output into another table. So the downstream applications can read from the output table. This is how we do applications using batch and ETL. This is going to be the same philosophy, right? But what is the difference? There is no batching, actually. Everything happens. If a new event happens, the engine is going to process, going to flush the output, and the display is going to be updated automatically. All right? This is the same philosophy, for example, we have Confluent has a customer that, for those of you that are into games, you're probably going to recognize it. Fortnite, for Epic Games. So all the telemetry of Fortnite is basically running into Kafka using this architecture over here. It's about 2.5 gigabits per second of events flowing through Kafka and being computed and reprocessed in near real time. So Fortnite works like this, right? Lyft uses the same strategy as well. Lyft actually is a customer from Confluent. Uber uses the same strategy, although they are not customers, but they use Kafka and they do basically the same thing, right? So as you can see, applications these days are using this philosophy, all right? So as developers, as Java developers, eventually you might face some company or projects that will ask you to implement things like this, right? So that's why I think it's important to present the concept of event streaming applications, all right? This is the architectural view, and finally, we're going to discuss the implementation view. But the way I like to present this, right? Let's not talk bits and bytes as of now. Let's see how this is going to be deployed, right? So, if you want to try this by yourself, just clone this REPL. I'm going to clone it right now because I need it. Everything is there, right? So everything you need to do is there. So let's do this now. And you can see, and then we can, the deployment kind of takes about 4 to 5 minutes. How many of you have heard about Terraform? Good, because pretty much all the code that does the deployment is written in Terraform, right? For those of you that never heard about Terraform, I can explain, right? Actually, this presentation and demo is interesting because it introduces you not only for the Java pieces of the application, but all the ecosystems that usually we use for deploying this type of application. One of them is Terraform, all right? So let's start with the clone. I think I have to clone my wrapper here. I haven't cloned it already, but I like to do from scratch so you can see how it goes. So this REPL is called demo scene, all right? Pretty much what my team does for developer relations, we create the demos and we flush into projects over here. For example, if you want to see how to do CDC and pulling records from a database and bringing this to Kafka, there is a Connect JDBC demo that does this. So you can kind of see how the code does and everything like this. The PacMan demo is this folder over here. We call it PacMan Cloud. So the instructions are all over here, all right? I'm not going to pass one by one because I created this demo, so I know by the top of my head, so I'm just gonna do it right now. So first step is cloning the repo, right? Usually what you're going to do, font size is okay? Maybe like this?
Yeah.
Right? Right, so let's do, I'm gonna start this in my temp folder. I'm going to create a good, so SD jug. And I'm going to clone it here. Hopefully it's going to be fast. The first time I presented this, I was using, there was no internet in the conference that I was presenting, so I used my phone for, imagine cloning this whole repo using my phone, so it took a while, so at least now it's fast. So the project is demo scene, so I'm going to open this on my Visual Studio Code. I know, I've heard this before, it's not the best IDE for Java development. I realize this, but I kind of like it, Visual Studio Code, so that's why I'm using it. Mostly because sometimes I have to work with other things that's not Java, so that's basically the reason. TMP, right? SD jug, demo scene. All right. Let's play. So the folder is PacMan Cloud. Where are you? Here he is. Okay. So do I need to increase the font size a little bit or like a little bit more? Like this? More? Okay? All right. So the very first step you need to do, everything as I told you is written in Terraform. Terraform does the deployment of the code, right? As well as the creation of some cloud resources that I need for the demo, right? I'm going to explain the implementation view later, but long story short, I need some compute instances, I need some load balancers, I need some buckets running on the cloud provider. So everything that I need is being created by Terraform, right? Terraform is a very good strategy for you, kind of a blend deployment code, your jar files, your Maven project, something like this, with infrastructure that your application is going to need. All right, so you can kind of create the end-to-end architecture as immutable infrastructure. What I mean by immutable, you can create. If someone goes there and change, you can simply apply the change, and it's going to make sure the architecture is immutable. Right, so it ensures consistency of your software. That's basically the practice. So Terraform, I have 3 implementations right now. I have for AWS, for Azure, and GCP, right? Usually I ask people to choose between one of them, but I'm going to strategically use AWS for this demo right now. Not because I'm a big fan of AWS, actually I like the 3 of them, but because recently AWS is the only one that I have actually implemented a serverless implementation, which is pretty cool if you think about it. For Azure and GCP, they're still spinning up compute instances, block volumes, kind of it's not truly serverless. I still have to sit down and refactor the code for being serverless. I know how to do it, but I have to have time to sit and change. Or if some of you want to help me, I accept some PRs on the repo as well. So I'm going to pick AWS, and you're going to see that there is this 2 files here that one of them is obviously, in order to create resources on AWS, you need to provide your API key and secret to AWS, right? It's kind of expected. And the other one is, where is your Kafka cluster, okay? So let's start with the cloud provider. I have a copy of my credentials. Staging directory, I think, so yeah. Work, staging. where's the name? Cloud. Yeah, Cloud var. I'm going to store this on PacMan Cloud, Terraform, AWS. Okay, so here is the file. I'm not going to open this file because it has my API key and secret, and we are being recorded. So I don't want to retire my API key and secret. But trust me that we have, this file is basically this, but has the value over here. All right? And this one, I'm going to purposely rename to remove the examples. So for those of you that don't know Terraform, if you want to provide variables, like environment variables, to your code, basically you create this file called .auto.tfvars. So this is how you externalize all the values that you need to provide as input, right? And the Terraform code is going to use that, so you don't need to explicitly set this on the code itself. You can externalize, right? So we need to provide these values over here, the bootstrap servers, the API key, the secret, schema registry, and all of that. So because, and only because, this demo is going to run in the cloud, I'm going to create a Kafka cluster that also runs in the cloud, all right? But strategically for this example, if you are dealing with an implementation that doesn't necessarily run in the cloud, you can come up with your own Kafka brokers, bootstrap servers that run on-prem or whatever you want to run, okay? The only difference is about, think about it. If I run this Kafka broker on-prem in my laptop and the whole application runs on the cloud, there will be some latency in the communication, right? So we call this the gravity principle, right? Both of them have to be co-located so you can minimize the performance of the network communication. So I'm going to create a cluster real quick over here. Remember I told you that Confluent creates a service called for Kafka, so developers can start using Kafka without necessarily installing it and using it. So I'm going to use this service. We call this Confluent Cloud, and internally, we call this, the project internally that we call serverless Kafka. And AWS, right? I'm not going to use this Fargate cluster, I'm going to create a new one. We call this SD jug. We call this serverless Kafka because region, I think California would be interesting, because you literally use Kafka as a service. So you don't necessarily have to install the brokers or maintain the brokers or create an infrastructure for this. You only pay by the hour. Just like you would do, for example, for AWS DynamoDB or Google Big Tables or something like this. You start using more the software rather than maintaining the infrastructure for the software, right? So that's basically the beauty of it. So I'm going to create a cluster, and here we go. If you're creating clients for this cluster, which obviously I would presume that would be written in Java, right? Makes sense, right? It's a Java user group. You would simply create an API key and secret, just like I'm doing here right here. And you won't jump straight through the Java one. So it generates for you all the properties that you need to set for communicate with Kafka cluster. So if you never worked with Kafka, Kafka works just like this. To create a connection, you have to provide a set of properties, right? One of these properties is the endpoint of the broker, which is this, right? And a bunch of others properties that basically dictate timeouts, communication exchanges, if it's going to be SSL enabled or not SSL, etc., right? You provide the properties and you create a connection from it. That's how it works. This is what I'm doing in the Terraform code. So I'm going to copy this and put it over here. Okay. The API key is this, which is my username. Not actually username, but how I'm going to identify the application for the cluster, right? And this is the secret, which is not any secret anymore, right? Okay. And same goes for, let me do this. Same goes for schema registry. So schema registry is, have you heard about schema registry, by the way? Okay, let me explain. That's important. Although this implementation doesn't actually use this schema registry, but I'm going to explain anyway. Let me just generate an API key and secret for schema registry, which is this. And put it here. And let's start the deployment. Terraform, AWS. So if I run Terraform plan, actually Terraform init, that's the first thing you need to do, because all the code, I'm going to walk through the code, don't worry, all right? But in the code, Terraform code, we use plugins for doing things, right? So in order to make Terraform make things lightweight for you, you only provide the code, and by the time you're actually going to do the deployment, you type Terraform init. So it's going to scan all the plugins that you have used throughout your code and install it locally for you. All right, so you don't have to actually keep running around with your plugins all the time. So now that we have the plugins installed, I can create a plan, right? A plan is essentially Terraform verifying in the cloud provider if anything that I have mentioned here in the code is already created or not. So it can have an idea about how many items to create. All right? And finally, you can simply type Terraform apply minus auto approve, and now the deployment is going to start. Okay? Because it's going to take about 5 minutes, I'm going to take this time to, number one, explain what schema registry is, right? And secondly, walk through the code so you can understand what I have done here. Okay? Once it's deployed, we can start playing with the Pac-Man game. So, back to the schema registry thing that I was mentioned before. You know what this is, right? Which is building right now, Maven. So this is my function that I'm deploying right now. Kafka has no format, okay? There's no predetermined format for Kafka. Anything in Kafka is an array of bytes, right? Your producers, when they write data into Kafka, they basically come up with an array of bytes. The consumer, when they read data from out of Kafka, it's an array of bytes, okay? Kafka has no format predetermined, right? It's different, for example, for JMS. In JMS, we have text messages, or map messages, or object messages, right? We have different type of formats that we can specify in the message. Kafka is an array of bytes. However, you can actually determine a specific format for your messages and records in Kafka, right? We use a framework called Avro, which is from Apache as well. Avro is a way for specify a schema for your records and messages and all of this. And then you can actually serialize and deserialize records based on the schema that has been written in an Avro format. Okay? Think about this as in a database, every table has a DDL, right? Data definition language. That's the schema, that's the layouts, number of columns, the data types as well. Avro allows you to do the same. Okay? So you have to have a way to store your schemas, right? Where are we going to store this? You're not going to store into Kafka per se. So that's why we use schema registry. It's a registry for your schemas. Okay, go ahead.
So data is input into the
Kafka.
schema or Kafka.
Yeah.
It's already in bytes.
Everything is in bytes, exactly. Yeah. Yeah, that's a good question though, because regardless if you use Avro or not, in the end of the day, the record in Kafka is going to be an array of bytes.
So for example, you're inputting a value into an attribute.
Mm-hmm.
So it's going as you're inputting it, but you're not inputting it as a byte. It's already transferring it to
If you don't use schema registry and Avro, yes, you would have to come up with your own serializer in Java that's going to come up with your object, instance object, and doing serializing to bytes. But schema registry and Avro has a Avro serializer and deserializer that does this automatically for you. So as a Java developer perspective, you are going to write into topics, basically providing an object, and the serializer is going to do this magic for you. Right? So you don't, in other words, you don't have to actually worry about this, unless you are serializing and deserializing using other formats other than Avro, which is possible. For example, people that actually develop this and using Golang, for example, they usually don't like Avro at all, because Avro is more like for a Java, Word type of things. They like to use protobufers. So protobufers is another way to specify schemas and to serialize and deserialize data. So you can do this. You just have to write down your own serializer and deserializer, right? Okay, so schema registry we covered. I told you that I would come back to the implementation view so you can understand what's being deployed here. So let me explain this right now, and then we can walk through the code for how I implement this. Remember the architecture view? We did have an application actually running on your mobile and laptops. So this application, the way I did, is essentially I create a bucket in AWS, okay? The whole Pac-Man game is a bunch of HTML, CSS, and JavaScript files, basically, right? So what Terraform is doing right now is it creates a bucket and uploads all these CSS, JavaScripts, and HTML files into that bucket. This is your application, your front end, per se, okay? Remember I told you that application, all the events basically call an API, right? So what Terraform is doing is essentially creating an API gateway in AWS, right? An instance of an API gateway, and it's deploying a Lambda function that I've written in Java, right? So every time an event calls the API that has been exposed by the API gateway forwards that request to the Lambda function. So it creates a new invocation to that Lambda function, and this Lambda function does one job only, which is write data into a Kafka topic. Okay? So let me show this Lambda function so you can see how a producer code looks like in Java, of course. It has been deployed. Look at that. It finishes. It took less than 3 minutes, right? Go ahead.
So before we go to the next step, I'm wondering, so the API is created by you or is created by some others already created and you just need to deploy it, right?
When you mean API?
The API gateway. Yeah. So,
Yes, this guy over here.
Yeah. So is that already created by you or?
Yes. Yes. So I've wrote the code in Terraform that spin up a new API gateway in AWS. Yes. Technically, you don't need an API gateway so the application can invoke the Lambda function, because you can expose the Lambda function as an HTTP endpoint, technically speaking. All right, but it is an architectural best practice to never expose your functions directly and put an API gateway in front of it, because the API gateway can help you, for example, do security on perimeter. For example, requests coming from the API gateway, we can apply some throttling strategies on the API gateway level, as well as we can do SSL termination on the API gateway. So until the API gateway is SSL protected. For the backend, everything is non-SSL protected. So it's more like a best practice to do actually than, oh, we need an API gateway to work. It's more like a. Okay, so Java code. Yeah.
But you're running low on battery power.
Do I?
You're at 16%.
Well, it's not. Plug it in.
Or maybe it's
Huh. Maybe this outlet here is
I
not
just
working.
tried switching those when you were talking, but
Did it work? Yeah, it's not working. Glad you pointed that out, because we would be interrupted in the middle of the presentation.
do we have another one?
Let me see.
There's one on the desk, the white box.
Maybe. Oh yeah. Yes.
All right.
Now we're good. Thank you for brought that up. All right. Java code. So the implementation of the Lambda function, it will be, of course, Terraform, AWS. You see where it says functions folder? So basically within this folder, I have a Maven project created, right? You can just generate a Maven project out of scratch. And then in the POM file, the dependencies that really matter is, because I'm creating a Lambda function for an AWS, you have to do this dependency here for Lambda Java Core, right? As well as, this is the most important one because it allows you to have access to the client's API from Kafka, right? With currently, this is the last version, 2.3.1. And Login4j, because which Java developer doesn't love Log4j, right? So basically that's what I'm doing. The code is this, I call event handler. So let me walk you through in this code real quick, and then I can show you the rest of the code in Terraform. So this function, as we call it, basically implements this interface called request handler. So I am a lazy developer, I have to confess, all right? Technically speaking, the Lambda function API for Java allows you to declare your own POJOs for defining the request and the response, right? You can come up with your own Java class that would design your request and response. Or you can simply treat them as map of string and objects. There's an array of like parameters that you can provide with. So I've chose that approach, but bear with me that you could have also be more elegant in your code if you wanted. So essentially what I'm doing here in this method handle request, I am, you see this object over here that I've called, where are you? Producer. So a Kafka producer is basically, as the name implies, is the code, is the object that you are going to use to write data into Kafka, right? So because I'm using functions, you have to program your functions to always check if the, where is it? Okay, here we go. Ensure producer is ready. You always have to make sure the Lambda function has been properly initialized. Why is that? Functions has no context, has no state, right? They spin up Docker containers on demand, so you cannot ensure that you have this global variable instantiated all the time. So if producer is new, it means that somewhere AWS spin up a new Docker container underneath and you have to initialize all your producer all over again. Remember I told you this basically is passing properties to it? So passing properties, create a producer, passing the properties as a constructor parameter, there you're good to go, right? So what the function does is essentially picking up the body of the request that's being sent by the API gateway. There's a string, essentially, right? From the query parameters, I'm figuring out what topic needs to be written, right? There will be a bunch of topics that I can actually write data, so I'm picking up which topic to write by the query parameters, and I'm sending, you see, the topic and the event to the producer. That's how I am producing data into the Kafka topic, all right? So let's make this theory to test. So let me pick up this endpoint over here, and I can use this for now. Okay, and then I'm going to ask you to scan. Let me generate a barcode so you don't need to write everything. All right, so if you care to scan this barcode, this is going to be your application that you're going to play Pac-Man. All right, so just scan the barcode and you can play. Because I need for you to just play a little bit so I can see if events are actually coming and being written into the Kafka topic, right? And then we can move forward. So like 3 minutes or 2 minutes for playing part. Go ahead, go ahead. Go ahead.
Yeah, so meanwhile, I have a question for the topic. When you try to use the parameter as a key, so how do you associate the key with the topic?
Good question. When you produce records into
Yeah.
Kafka, you have the option to specify a key
Yeah,
besides the record, right?
okay,
The way I've done here,
yeah.
purposely,
Yeah.
I am not specifying a key,
Mm-hmm.
okay? Because I am doing this in the string processing part that I'm going to show you later.
Yeah,
So I'm re-specifying the key dynamically. But I could have like specified the key by the time you were producing. I could have.
okay.
All right. So basically, you would set this over here. Let me show the code. There is this method send has an overloaded version of it,
Yeah.
where you can provide the topic, the event, and the key.
Yeah.
So actually, there's multiple versions of this overload. That also that you can specify the partition as well. So yeah, basically, you would provide a parameter. But I'm not doing in this case over here.
So it is smart enough to figure out by the function itself, right?
By what?
By the function itself. I mean, we'll call send.
Yes.
Exactly which topic I'm gonna connect to. I'm gonna send to.
Yes. Yes. It's working? Are you guys able to play with?
Yeah, I'm playing it, it stinks on it.
Let me see. If I have topics, that means that you guys are playing. Let me see. Print user game. Yep. Those are the events coming from your phone.
Chris.
After we process all these events with the streaming engine that I told you, this is going to look like better, more like a table than actually a bunch of streams coming in, right? But before we move forward, let me highlight this fact over here that I think is very interesting. Every line of this is an event, obviously, right? And you see that you have this column called user, which holds your name. And there's a column called game, whose value is basically a JSON payload. You see? The value of game is a JSON payload, which in turn has the columns score, lives, and level. Right? So keep that in mind, that we have a very simple field that's basically the value is a string, but we have another field called game, whose value is a complex data structure. It's not a flat value, right?
So is that
It's like
Go ahead.
what is you have key value, so that's the object part? Is it like
Correct. Very good question. We have a key value. You were right. However, can you see here that the key is null? Because as I was explaining to him,
user is object?
yeah, the user is basically part of the value.
Okay, okay.
Yeah. So all of this from here
So
to
that
here
is the object.
is the value. So I'm generating events without a key, purposely,
Okay.
because I'm gonna actually set the key dynamically in the string processing. But I was mentioned to him, I could have generated a key because I have the information. It's basically your user. That's your
So the one when you print,
key. Mhm.
you said Kafka, the storage is byte,
Yes.
and what it's sending is in Avro format or whatever. So, but you see here JSON, so there is
Yes.
another layer that translates between Avro to JSON structure.
Good question. And when I was explaining the Avro part, I was basically explaining in the context to explain what schema registry is. But, thanks for bringing this up. In this particular case, my value has been specified as a JSON payload. So I'm using JSON here in this example. I could have used it JSON, CSV, XML, whatever. You know, the value itself is an array of bytes. So it's up to you to specify whatever data format you're going to use. It doesn't need to be Avro. Avro is the most common practice because you can do schema versioning, schema enforcement, etc., etc.
Okay.
You know, but it's a string. It's basically a string.
And there's like no limit to the number of bytes for instantaneous streaming?
Good question.
Buffering
So let me see how do I explain this. Technically, there is no limit, but we all know as developers that there's always a limit, right? There's always a limit. There's always a point where the architecture will be finite. So the way Kafka stores data, it uses disks, right? So when you create a Kafka cluster, you spin up a lot of brokers, and each brokers in their own machine are pointing to a volume, to a disk, a file system per se, right? So your limit is going to be dictated by the amount of disks that you have in a Kafka cluster. So for example, imagine that you have a Kafka cluster with 4 nodes. Each node has 1 terabyte of data, all right? So you would have a conceptually limit of 4 terabytes of storage to write data. So there's a limit, you know? But why I told you that we have no limit? Because every Kafka node has your own storage. So you can scale out your architecture and storage by putting more Kafka brokers in the cluster. So you can increase the limit. It's different from a database where all the database instances are pointing to a shared storage. You see? That's a different architecture.
Is the plan to eventually take all of the content that you're moving through your Kafka brokers into a permanent store?
Good question. Actually, no. The idea how Kafka was designed was to use the disk as a storage layer. So why is that? Because it's cheaper. Because different from other technologies like databases, the disk for Kafka brokers doesn't have to be, for example, solid state disks. In a matter of fact, we enforce to use magnetic disks. It's better. It's cheaper, of course, and it's better for Kafka performance, believe it or not, because of the data structures that we use to store data in the disks. Yeah. Go ahead.
Yeah, so you mentioned if we have 4 brokers,
Yeah.
Kafka brokers, and each one has 1 TB, and total we have 4 TB, that means no duplicate data, right?
Not necessarily. You can have duplicates.
Yeah, that's my question. If we don't have duplicate data, what if one of the broker was bad or somehow?
Okay, let me just
lose all the data.
let me just understand what you mean by duplicates. You mean replicas?
Yeah.
Oh, okay. Yes. So replicas are kept in memory.
Redundancy,
Kind of
redundancy or?
Yeah. So each broker. But we have this concept of partitions, right? You create a topic and you break down the topic into multiple partitions. So each partition is spread over in the cluster, so where you store your replicas. But the replicas are not kept in disks, are kept in memory, because it's a replica, right? Your primary partition is on disk. Okay? So you can retrieve and recover the partition much faster without reading from the disk all over again. You can. Go ahead.
It's because of the memory utilization.
Exactly. Yeah. We do this because in Kafka, I'm not sure if you know this. Kafka doesn't use the heap memory of the JVM to store data. We store this off heap, right? So that allows us to have pretty much no garbage collection on JVM. A typical JVM for a Kafka broker is 4 gigabytes tops. We don't need more than this because all the data is stored off heap. So we can have bunches of data allocated in memory without necessarily having a garbage collector penalty for this. So that's why we store the replicas in memory. So it's fast to retrieve.
Wait, it's not stored in heap?
No, data.
Yes. But is it dynamically allocated though?
Actually, it's not dynamically. When we explain, it's very simple in the end of the day. You know that Kafka is persistent, right? Every record that you write into Kafka goes to disk, right?
Is that required, or can you run this all in memory?
You actually cannot even disable this. That's the basically behavior of Kafka. All the records goes to disk. That's how Kafka was designed. And because it goes to disk, have you heard about the OS operating system cache? The cache of the operating system, right?
L2 and that kind of stuff?
Exactly. So there is a 85% watermark that all the memory that you have in a specific node is dedicated for OS page cache. It's where we store data. Because think about it, if the data is on the file system, we have a copy of that file on the OS page cache. That's where we store actually the data in memory. So we have more density of allocation in terms of memory without necessarily compromising the JVM. Because what's the problem of most messaging technologies that rely on the JVM to store data in memory? We eventually run into a situation about garbage collection, right? That's the problem of allocating data on heap. If we allocate data off heap, we get rid of this problem. Go ahead.
Yeah, so you mentioned the Kafka use memory data. It even give me more concern, like how we can make sure that, like each nodes, they have a same copy. So say I want to update some data. I update 3 times. First time, first name, second time, last name. And the first name goes to this node, right? This
Yes.
Kafka node. And last name goes to another one. And maybe something else goes to another one. So how we can make sure all these changes are go to the same data? And how we can make sure what if the last name, this one for somehow is got broke?
Oh, got it.
And those data was lost.
So, good question, good question. The answer to this question is this, by specifying a key. So, one topic, let's call the customer's topic, right? When you create a topic, you specify the partitions of that topic, right? How many slices of that topic you are going to create. When you produce a record into Kafka, right? Let me use your example of first name and last name. So the first record you produced was the first name, right? You use the key 1, okay? It's going to end up in a given partition. If you produce the last name record that is an update or something like this, using the same key, which is 1, Kafka ensures that's going to end up in the same partition. And that partition will have replicas across the cluster. So our unit of replication is not per record, it's per partition. We replicate the entire partition instead of replicating records, right? Why is that? Because if you keep replicating each record, we're going to have a multiplexation of communication across the brokers that's going to saturate your network. So instead of, go ahead.
Yeah, so how about the 2 times I both update the first name, and then I update very quick. How we can make sure the last time I updated gets saved?
You don't. If you don't use the transactional API, for example, you don't. It's going to be a FIFO, first in, first out. But you can create transactions just like you would do in a database.
Normally it's first in, first out, but since we are in the clustered area,
Yeah.
so my both transaction, both update the first name,
Yeah.
it goes to 2 nodes.
Correct.
And then how I can make sure the second node always save last? They almost got the same time, so it's pretty much.
So again, first of all, you have to use the same key to ensure that's going to be in the same partition. The write in the partition, either if it's one write or multiple writes, is going to be atomic. All right? So you ensure that's the same partition. Once the write is done, that's where the Kafka cluster is going to replicate that partition, not the records, but the partition across the cluster. Right?
Yeah, but what I'm saying is, for my part, I always make it atomic.
Yeah.
But for your part,
For the cluster.
The first node, I don't know who gave my first request,
Uh-huh.
right? He got request, he have to for somehow save to somewhere, right? Save to his disk or.
Oh, got it.
And the second one got another update,
Mm-hmm.
and they got almost same time. So it's hard to decide, okay, second one save last or second one save first.
Yeah. No, you're right. You're right. If you don't do anything, that's what's going to happen. So it's going to be a mess in terms of storage. But as I told you, you can, because you're giving me an example of use case that requires consistency, data consistency,
Yeah,
right?
that's what I'm saying.
So that's why you would have to use the transactional API. So, but using the transactional API in Kafka, you would create a unit of work, update, delete, delete, insert, and that unit of work is going to be fully committed or fully roll it back. But you have to write the transactional code for this. Otherwise, it's going to be random.
I guess my question is like, normally for this case, for cluster, since they use memory to save data, so we may, for somehow make them like either use a shared memory or some way so they know each other. Okay, I got this updated first or something. But if they are only just work on for their own, like use their own memory or use their own disk, then that may be an issue. That's what I'm saying. Because my queue request goes to node and they don't know each other. They just say whatever they want.
All right, so,
I guess that's my
yeah.
question.
No, I think we're getting there,
It's not
like,
about transaction. It's about,
if I lose a broker, I'm going to lose the data. That's what you're saying?
yeah, I mean, that's
Bec-
another issue, yeah. The
Yeah.
broker all may die if they only work for themselves, they have their own memory, they have their own disk, and if they die, if one of them die, nobody else, no one else knows what is his data or what is his.
Yeah, but that's where the replicas come into play. Like, for example, the partition is the unit of storage, which goes to disk in one specific node, right? But you can say that a specific partition are replicas across the cluster. And those replicas are going to be stored as a backup in the other nodes. You can say the replication factor is 3, 4, 6 times. So you're going to create replicas across your clusters. And those replicas, optionally, can also be persistent if you want it. So instead of the replica being only in memory, you can say the replica is going to be persistent as well. And I think that's where your question started, because it all boils down for the amount of storage that you would have in your cluster, right? So if you say that your replicas, not only your primary data, but your replicas are going to be persistent as well, that means that you have to size your cluster to be the double or the triple of what you were expecting in terms of volume. So it's a sizing exercise. For example, if I'm wondering if 6 months of data is going to come up with 1 terabyte, that means that my cluster needs to be at least 3 terabytes of storage. Double plus 1.
So at this point, I'm going to suggest that we just take a break, maybe a 10-minute break.
Yep.
If you want to continue the conversation during the break, but everyone else, let's stretch, get some pizza.
Let me
Come
just-
back for the second half.
Let me just make the question.
Oh,
It
sorry.
is someone playing right now?
Yes.
Okay. Okay, go ahead.
I love seeing this.
Yeah.
Just keep on scrolling by.
Yeah, go ahead.